Welcome everyone to the multi-armed bandits, and now we're gonna learn about an algorithm that tries to be optimistic in the face of uncertainty, and by doing that learn about the expected rewards of the treatment arms. So the more uncertain we are about an action value, the more important it is to explore exactly that action. It could turn out to be the best action. Yeah? And so if you take a look at this figure here, we have three arms where we have the mean rewards that we have estimated, and they are estimated with uncertainty. So we have a lower bound and an upper bound. And because we want to get at the best mean reward, well, let's just ignore the lower bound and focus on the upper bound. So if the distance between the upper bound and the mean reward is larger, then, well, we have an opportunity to explore that arm. So let's pick arm number 3. And after picking arm number 3, we are more certain about its value. So then we might explore another arm. So the idea is to always pick the best arm. And the best in this case, for this algorithm, means that we want to exploit, we want to, take the one that has the highest average observed reward. And also we want to explore. So we want to see, well, the arm where there is a lot of uncertainty, that's what we want to explore more. So imagine we would have an oracle, no perfect knowledge about the upper bound, and we could just select always the arm with the highest upper bound. Then this theorem says that we would converge to the best action. Why? Because, well, if we repeat infinitively often the experiment and always choose the upper bound, then this upper bound will be so tight around the mean reward that it will actually equal the mean reward. And suppose that we would converge to a suboptimal arm, A, after those trials. Then the upper bound would be so close to the mean reward of that A option that they're the same. And for the other arms, if we play them also very often, infinitively often actually, then also their upper bounds would be equal to their mean rewards. So what we would observe is then that the upper bound of the suboptimal arm A is greater or equal than the upper compared to the upper bound of the other arms. And that would imply that also the mean reward of the suboptimal arm would be greater than the mean reward of the other arms, all the other arms, which cannot be by assumption because we assume that A is suboptimal. So that shows that we will always converge to the best arm, A star. Now, the problem is that we can't compute an upper bound with certainty because we're doing experiments, we are sampling. And there might be always some uncertainty left because we might not have a representative sample, for example. So we need to come up with a way that gives us, even though we have the uncertainty, and a strategy that works by selecting the upper bound. So what we do in practice is we estimate an upper confidence bound, UT, for each action value in each time period, such that with high probability, that estimated mean plus this upper confidence bound is greater or equal than the true success rate. Now, the upper bound actually depends on the number of times we play that arm. So if we only play a few times the given arm, then the upper bound will be very large. If we play it very often, we have little uncertainty, and this UT will be very small. Now, what we do is then we take this combination, the estimated mean plus the uncertainty bonus, and we select the arm that has the highest value of the sum. Yeah. Because this is probabilistic, we need to use a theorem from statistics, which is Hoeffding's inequality. And that is going to be useful, as we will see in a second. So imagine you have random variables that are identically and independently distributed, x1 through xt, and they're all binary. They take values either 0 or 1. Then we have the average. The sample mean is just calculating the sum divided by the number of trials. Then Hoeffding's inequality says that the population expectation of x is greater than the sample average plus the uncertainty. Yeah? And the probability of that being the case is smaller or equal than the exponential function to the power of -2 times t times u squared. And this u is again the upper bound. So we have the upper bound on both sides. And we make use of this. So instead of the t, we include the number of times we played a given arm. Instead of the sample average x bar t, we put in our estimated mean reward. And instead of the u, we put in our upper bound for each of the u's. And the q of A will be the population success rate. Now, this is great, but we need to put a little bit more structure on the right-hand side. So let's take a look. Well, we can just say that we want with some probability p, we want this right side to hold. So what can we do there? We just pick a probability and solve for the upper bound, ut. So if we do that, we get the expression that ut of A for each arm is equal to the square root of minus log p divided by 2 times the number of times this arm has been played. And here we see if you play more often, this upper bound gets smaller and smaller, so the uncertainty vanishes. In contrast, if this p gets larger, then, well, this uncertainty bonus gets also larger and we play this arm more often. Now, this p actually turns out to be a tuning parameter, a hyperparameter that controls the exploration-exploitation trade-off. Now, typically people use p equal t to the power of minus c and set c to 4. Yeah? So that means that the more we play, this actually has a log t function. So if we play very often, then actually this ensures that we get the optimal arm. Now, why does it do so? Because, well, as we said, that if you increase in time, then you're more likely to explore each and every arm. But if you play more often one arm, then the uncertainty bound reduces and we play this arm not as often. So the upper bound with this parameterization is then square root 2 times log t divided by n t of A. And in an empirical example or numerical example with a t equal 100, we can see how this looks like. So here we have just 3 arms with 30, 50, and 20 pulls. The empirical mean is 70%, 50%, and 60%. And now you see how this number of times this arm has been pulled factors in the exploration bonus. We can plug that in and calculate this, and then calculate the UCB value that is the basis on which we select the next arm. And here, this value is highest for arm 3, so we pick arm 3 for the next session. The algorithm looks like we see here. So we initialize everything, we repeat then the algorithm t times by executing this upper confidence bound value from which we calculate and from which we then select the arm that has the highest value of this. Then we receive the rewards and update our empirical estimate and also our action values. And we do that repeatedly. Now, how does the exploration and exploitation work here in the UCB example? Well, it's a clever way of reducing exploration over time because we estimate the upper bound on the true action values. So we want to do that. Here is a picture where we have the parameter c equal to 2, and we can compare the epsilon greedy to the UCB, and we see here how this c would change the exploration a little bit. We could try different c's, for example, but we see that it's a sublinear regret. Now, exactly that is the convergence properties. So although Hoeffding's bound is probabilistic, UCB does converge. And the idea is that as we play more often, the term, the upper bound term increases, ensuring that the arms are tried infinitively often. And the higher the number of pulls is for a given arm, the more confident we are in that estimate for that action. So the expected loss is logarithmic. Here are some references, and just to summarize what the upper confidence bound does is it's a probabilistic upper bound that helps us reduce uncertainty and decrease exploration. At each time step we have exploration bonus plus the empirical mean, on which we select then the next action, and it ensures that we play all the actions and we converge to the optimal arm, achieves logarithmic regret, and often performs better than the epsilon greedy strategy. Thanks for watching. See you in the next video.